Over to you, Sarah.
Okay, great. Thank you, Kevin. I will start with hi, everybody. I'm Sarah Chappell, and I want to start with introducing us a little bit more, who's been today. So like I said, I'm Sarah. I was born and raised in the Shenandoah Valley in Virginia. My undergraduate was in geographic science at James Madison University, and then my master's degree specialized in chemical oceanography at Coastal Carolina University. Before joining DEQ about a year ago, I spent 5 years on active duty with the NOAA Commissioned Officer Corps as a hydrographer, surveying the ocean to update nautical charts. Ruth, who is going to take over partway through the presentation, was also born and raised in Virginia. She completed her bachelor's degree in environmental sciences at the University of Virginia, where she served as co-president for the Environmental Sciences Organization. And she has been with DEQ since 2018. And before I move on, I do want to point out that we do not have a typo on the main slide. Interestingly, the spelling of Gage, G-A-G-E, without the letter U, has a history dating back to the late 1800s within the United States Geological Survey, who we partner with. So now that I've got that cleared up, as for the rest of our office, 6 of us make up the Surface Water Investigations team, which is based at a field office, as Kevin mentioned, in Charlottesville. We have approximately 50 years of combined experience in hydrology and are currently responsible to operate and maintain 69 stream gauging stations throughout the Commonwealth. This map shows the location of our gauges ranging as far west as Blacksburg, as far east as Williamsburg, and north and south to the state borders. We work in cooperation with the United States Geological Survey and their National Water Information System to measure, calculate, and publish river discharge data. Many of you may be familiar with the USGS website, which houses our data. This is a screenshot of a discharge, and this one is of gauge height for the James River. Whether you use it as a work reference or maybe to determine when it's the best time to take a float trip down the James. And so we want to explain some of the terms that you see on the website and that we're going to use with you all today. And at the risk of insulting anyone's intelligence, I do want to start with explaining that hydrology simply means the study of water. Other terms that you will hear today are stage or gauge height, and those are interchangeable. That is the water depth reference to an arbitrary datum. All of our gauges measure and report gauge height, which has a relationship to the depth of the water, but is not necessarily the same as the water depth in the channel. For example, just because the gauge height at the James River was a little over 6 feet yesterday, it does not mean the water was 6 feet deep at that location. Just something to point out, it's a common misconception. Discharge is the volume of water that passes a given location within a specified period of time. We express this value in cubic feet per second, and it's represented with the letter Q. Stage to discharge relationship, we refer to as a rating. Put simply, the rating is a graph that illustrates the effect of gauge height on the computed discharge. Ruth is going to go much more into this shortly. So now that you're armed with a basic terminology, let's talk about what it is we do and why. This is a photo of me on a boat carrying a smaller boat, which houses a sonar unit, about to measure the discharge of the James River along the Blue Ridge Parkway. This is a definitely prime example of a wonderful, beautiful day in the field. Believe me, we've had several not so pretty ones. So in order to gather the information we need a permanent or a semi-permanent structure along the water that houses our equipment to make constant measurements. These stream gauges come in various shapes and sizes and house varying types of measurement equipment. Regardless of the style, every gauge records and transmits gauge height data by satellite in regular intervals. The majority of our gauges record every 15 minutes and then transmit those records hourly, which updates the hydrographs on the website, as I'm just showing you, or if you use an app, that information is likely pushed to that app. Our most common gauge structures are stilling wells, shown in the photos here. These are either made of corrugated metal, wood, or concrete. The upper left image is a picture of Ruth actually performing maintenance inside of one of these gauges. This image shows a more detailed view of what a spilling well setup looks like. The well measures the water surface by having two intake pipes, which protrude out into the river and enable the water levels to be the same in the river and the well. We then use a special float, steel tape, and a weight to determine the water level without having to measure it every 15 minutes, which would obviously be impossible without time travel and teleporting and all those fun things we don't have yet. Our more modern gauge structures contain pressure transducers, which are known as bubblers. Those use compressed air and tubing to actually sense the current water level based on the pressure. Our newest and best sensors are non-contact radars, which when these site conditions allow and the budget permits, which as many of you know can be rare, we can mount the radar to the bridge above the river, and it'll measure the distance from the water surface down from the bridge to determine the water level. So it's great to know what the water level is, but how does that help us know how much water is actually flowing? Well, we have to measure it. One of the ways that we measure this discharge is by wading into the river, meaning we physically get in the stream channel and divide it into 26 to 30 vertical sections. That is Ruth in the photo with our equipment there, physically doing this. To aid in the division of the stream into sections, we string a tag line with 1 to 2 foot increments across the river and then individually measure sections by moving a determined distance for each section. It's kind of a graphic shown below in the picture at the bottom of the screen. We then place a meter attached to a wading rod below the surface at 60% of the water depth. This is where it is determined to be the best approximate average velocity of that vertical section of water. We then let the meter take measurements for 40 seconds. Discharge is then calculated for each of those individual segments by multiplying the average velocity measured by the area of that segment. And then the final discharge value for the stream is the sum of each one of those segments together. Our stations are routinely measured every 6 to 8 weeks, as well as during high and low water conditions. These actual measurements provide confirmation or help us indicate and understand the need to change our ratings, which calculate those discharges when we're not present to do so. So what happens when we can't physically get in the river safely? If the water level is too high for a wading measurement, we use different equipment to perform high water measurements. Our top choice is an acoustic Doppler current profiler, an ADCP, as it's shown housed in that little boat. This uses the Doppler effect to measure velocity. I am not going to get into the Doppler effect today, don't worry. Please look it up if you're interested. ADCPs not only take less time to make a measurement, but they also enable us to measure during some high flow conditions that were not previously possible. Additionally, the ADCP provides a much more detailed profile of the water velocity and direction instead of just a single point measurement we would get from wading the stream. This greatly improves our accuracy of discharge measurements. Two other methods listed on this slide are handline, which is an older method, and then an even less accurate is a slope area method. And these two are only used when our other options are exhausted. These images show examples of a wading measurement, the top image, compared to an ADC measurement, the bottom image. You can see the significant level of detail in the lower image with ADCP data compared to only measuring that one single point in the water column to average the whole column as we do with a wading measurement. These two photos show two different styles of boats that houses ADP sonar units, which we then often lower over the bridge and manually move across the river, or sometimes we string a pulley system across and run the boats bank to bank. So I'm going to now let Ruth take over and explain what we do with the data we collect and how it's relevant to you and DEQ.
All right, great. Thanks for that, Sarah. Now I'll be discussing the data that we do publish in more detail, as well as some of the more challenging aspects related to our role, and then where that information goes. So this is a screenshot from the USGS real-time site where you can navigate through all of our data as well as the stations run exclusively by the USGS. And there will be a link to this site at the end of the slides. But the two main data values that our office publishes are gauge height and discharge. Gauge height can be thought of as an independent variable that gets transmitted directly from our gauges. This is continuously monitored, unlike discharge, which we need to calculate to publish. And it's important to mention that our data is provisional, which means it's subject to review by our team, which can be for a number of reasons, including equipment malfunctions, ice effect in the winter, as well as some mysterious animal activity that I will touch on more later. Every morning, our team examines each station for abnormalities or issues that arise, and then we go into the field as necessary to address them as soon as we can. Where gauge height is the independent variable, you can think of discharge as its corresponding dependent variable. It's derived from a rating curve drawn specific to each gauging station. And there exists a direct and positive correlation between the gauge height and the discharge, meaning that as one increases, so does the other. These two hydrographs of gauge height on top and discharge on bottom display that direct relationship. And you can see that though the y-axis scales and units are different, their shapes are practically identical. But before we can publish reliable and accurate discharge for a given site, we have to develop its rating curve. Put simply, rating curves are a stage discharge relationship that define discharge values based on the gauge height. And our continuously monitored gauge height gets transmitted by a satellite. Our rating curve will then determine what the discharge is for that gauge height. We draw these graphs in a logarithmic scale based on historical measurements made for the entire range and stage, utilizing more recent measurements weighted more heavily. They will occasionally have to be redrawn as permanent changes occur to a channel as well. Here is an example of a current active rating for our station on Stony Creek near Dinwiddie, which was drawn back in 2013. The x-axis will show our discharge in cubic feet per second, while our y-axis shows the gauge height in feet. Take note of the logarithmic scale, which means that discharge is increasing much faster with a rising gauge height than it would be on a linear scale. So for example, at a gauge height of 1 foot, the discharge is about 7 cubic feet per second. At a gauge height of 5 feet, it's about 467 CFS. And at 10 feet, it is 1,750 CFS. And this is the 30th iteration of Dinwiddie's rating since its establishment in 1957. So it has changed a lot over that amount of time. It would be great if we drew a rating and all of our subsequent measurements plotted right on it and confirm it. But what happens if a measurement does not line up with our calculated values? Well, assuming our instruments and equipment are functioning properly, this can occur for several reasons. Occasionally, major rain events will change the morphology or shape of the channel. For example, scouring can occur during rapidly rising events and require us to shift the rating more positively as more potential volume gets added into the channel for the same gauge height. By contrast, filling events will deposit more material into the channel and require a negative shift of the rating since there's less available volume for any given water depth. In addition to these shifts caused by stage events, seasonal effect also plays an important role, with leaves and other debris entering the channel in the fall, as well as increased algal and other vegetation growth in the summer. And as I spoke about before, animal activity can also require us to shift the rating. Looking back at the rating curve from before, you can see that the red line here represents a positive shift of the base rating, which is represented by the black line. And looking at these graphical shifts can be helpful to quantify data, but what do these changes actually represent in the channel? Well, first, any debris in the channel results from deposition, typically during a large rain event. And now that there's more material in the channel, a negative shift of the rating is required since there's less available space for water to fill. Debris can be deposited and removed again in a relatively short amount of time, as these photos are only a few months apart. In the top left, you see in December, our Robinson River at Locustdale. On the right-hand side, you see it in January, where just a few weeks had passed, but a large amount of debris had accumulated. And we had to shift negatively to account for that. But then in the bottom left, you see just a few weeks later, the same river, the debris has been removed, and a new positive shift is required to essentially cancel out the previous negative shift that the debris caused. Like debris, accumulated vegetation is also adding material to the channel, and so it will also require a negative shift of the rating to account for this. But this shift is much more gradual than those resulting from deposition events during rainfall. On the other hand, when a bank scours, such as here at our Big Otter near Evington site, then more potential volume has been added into the channel for the same gauge height. So this scour will result in a positive shift of our rating. And lastly, beaver activity can occasionally result in an artificial increase in our published discharge. This requires a negative shift to account for because any dams built downstream of the gauge create a barrier that traps water upstream and causes this unique rise in gauge height with no actual increase in flow. It is important to note that while the Office of Surface Water Investigations does not typically participate in water quality studies on a regular basis, our data is a vital foundation for many who do. The data from our gauges is used to help develop total maximum daily load values to keep in compliance with the Clean Water Act. This means that certain dissolved substances like nitrogen, phosphorus, sulfur, and some harmful bacteria must be found in concentrations below what would be considered harmful. Our office also provides required statistical information for special water quality studies. For example, we collaborated with Roger Stewart in the Office of Ecology and Craig Lott in the Office of Watershed Programs for their Clinch River special study in the summer of 2019 that focused on the effect of water quality on freshwater mussel populations in the Southwest. Our stream flow measurements helped quantify the samples they took, and if any of you are interested, I can reach out and, with their permission, share the preliminary results of that study. We do not publish real-time water quality data with the exception of temperature at a select few of our gauges, but there are a few USGS gauges throughout the state that do have these real-time data available, including the parameters listed here. But again, budget constraints. So why do we collect this data and who cares? Well, DEQ's Water Permitting Office relies on our historical and statistical discharge data to issue permits for withdrawal and discharge to residents, corporations, as well as water treatment plants. The National Weather Service uses our data for their forecasts and flood warnings. Civil engineers utilize historical gauge height and elevation data to determine optimal bridge clearance. Even home insurance companies view our data to designate prone floodplains. Recreationists depend on our gauge height data to determine if a channel is safe for boat transport. And finally, we assist with TMDL development and other water quality studies, as mentioned before. And with that, we are happy to take any questions you may have.
Thank you so much, Ruth and Sarah. That was a wonderful presentation and both out in the Charlottesville office. Good work. Do we have any questions that have come in, or does anybody out there have any questions for Ruth and Sarah? Go ahead and type them into the questions box here. Looks like you wowed them all. I don't see any. Oh, here we go. Took them a while to warm up. I'll let you guys handle the questions as they come in.
Okay, so the first question I see is, do you use continuous cameras to monitor for stream channel changes? That's a great question. We currently do not, but we have seen at the USGS, they have trail cameras that constantly keep an eye on their stations. We take pictures of the control condition during each of our site visits, and so we have those to reference, but that may be something that we'll be doing in the future. Yeah.
And then another question we have is, how often do we find ourselves having to update those gauge relationships? And so basically that's what we use the shifting for. So each time we go to the field and we determine that the measurement, we take a measurement in the water, that's when we're constantly updating those relationships. So anytime we're on site, we're coming back and updating those relationships. There's another question for, have you done any work in tidal waters? This office has not specifically as part of our regular operations. I know that USGS has quite a few gauges within the Chesapeake Bay area, but we are lucky enough to not have to deal with those extra complications in our work.
Along those lines, another question is, are our gauges part of the USGS system or in addition to them? We are affiliates with them, but we publish under their database. So I would say that we are part of their wider network. Do you conduct site-specific measurements on small stream for VPDES permitting purposes? Yes, but those are on a case-by-case basis, and typically we will have people reach out to us. And if we're not currently, measuring at some of our routine sites, then yeah, we'll try to fit those in. Absolutely.
Somebody asked, when did stream measuring program begin? We have data, I believe, as far back as the late 1800s in this office, but definitely early 1900s that we have records and boxes of up in our storage areas. Here's another question of, why do water levels last so much longer in the winter following precipitation? We're now at least 2 weeks later versus summer water levels returning so much quicker. David Evans asked if it was evaporation or what. I'm actually just going to go ahead and speculate a little bit that a lot of that has to do with the temperature of the ground and how much vegetation is growing compared to the winter. And then Doug Gilmer asked if we monitor precipitation and couple that data with our stream data. Yes, we actually use that to help justify what we see sometimes, especially if we can't get to a site or a location to take a measurement. If we know that there was a precipitation event nearby, we can assume that what we're seeing in the recorded data is real and not maybe a malfunctioning equipment or something. And then he also asked if we observe seasonal changes due to vegetation growth state, and that would be a resounding yes.
Yes.
between the growth in the spring, which tends to fill the channel,
we got another question. How many times per year do you visit each station on average? So as Sarah mentioned, we typically will visit for routine measurements between every 6 and 8 weeks. So I would say about seven visits a year minimum, but high water or any sort of problems come up. So that number's probably higher. And then we've got a question: when debris blocks a channel, is it sometimes removed mechanically by people, or does it more often just move downstream on its own? We have assisted in beaver dam removal in the past. So yes, if it gets bad enough where we can't make accurately good discharge measurements at that site, then we will attempt to remove it. But a lot of the higher stages will wash away some of the more minor debris piles.
We have a question on what is the smallest stream we can measure. Will Eisenberg says he guesses it gets harder, and that it does. And so we can only measure, we are limited by the depth of the water with our actual equipment. So if we can't put our wading equipment, even the miniature ones, in the stream, we can't measure that. But oftentimes one of the reasons our gauges are set up where they are is to help understand what is coming in from the streams, the tributaries coming in. Here's go ahead, Ruth.
We have a question regarding the beaver damage that they can cause. Has anything like a large tree fallen and hit a gauge? Not the house that I'm aware of, but just last week we had a reference mark get sort of dislodged by a falling tree. So yes, these things do happen, and that's why we run levels on a regular basis to confirm elevations. Luckily, our gauges haven't been destroyed by anything but high water.
And it looks like Zach asked if there are any plans for real-time water quality monitoring. There are no plans within this office that I know of that we are in the works on or anything, but I'd imagine working as closely as we do with other stations. And I know USGS, as Ruth mentioned, has water quality monitoring at many other stations. That may be a down the road opportunity, but just nothing right now in the works.
We've got a question about providing or verifying drought flow frequencies on small streams where gauges aren't present. I would say that we can extrapolate data based on some of our larger and more nearby channels, but if we don't have something on that stream, it might be difficult.
And Brian Campbell asked if we have our program staff assigned to a specific territory, or does everyone work across Virginia? And because there are just 6 of us in the office, we all work as a team and share the responsibility throughout the state. Each of us are assigned gauges that we actually take care of, kind of that back end of the data processing and updating those ratings and shifting to make sure that relationship stays appropriate. But all in all, we meet every morning in the office and decide what gauges need our attention that day, or we will go on. Back when we could travel to hotels, we would go on kind of purposeful field trips to get down to an area and get all of our gauges around the Roanoke area at one time, rather than having to mismatch them in. And so hopefully we'll get back to that soon. But we definitely share all the responsibilities in the small office.
And it looks like that's it for questions.
Yeah.
So
I think, did you guys, I see one here. Are there any, I'm not sure if you answered this one. Are there any plans to expand gauges to sample other water quality parameters? Did you answer that one? I don't remember.
So I would say not at this time, not at this budget, but potentially in the future, that would be great. Yeah.
Okay. Couple of minutes for any other last minute burning questions you all have out there.
Oh, are you seeing any data trends that may be related to climate change? I would say just frequency of floods or high water events. I think those are pretty suggestive. Sarah, anything to add?
Nothing that we can really point to. Of course, our long-term monitoring will hopefully help climate scientists, have that data to push these in the future. But as of right now, as far as otherwise, we see, we had a very dry time last summer, and now, like Ruth had said, we're seeing a lot more. But that's just based on, our limited scope and our ability here.
There's just 6 of you in that office doing all of Virginia, huh? Wow. Fantastic job. Well, I think that's all I think that's all the questions that we have. I've learned a lot today, and I'm sure the participants have learned a lot as well. I want to thank you, Ruth Diamond and Sarah Chappell, for giving us a wonderful presentation of DQ Talk today, and we'll be posting this on our DQNet page. And with that, I think we're going to call it done. Thank you very much, and enjoy the rest of your day, folks. I'm going to go ahead and close the webinar now.
Thanks, Kevin.
Bye-bye.
Thanks for having us. Bye.